Hello everyone, my name is Leopoldo and I'm here to present our work on detecting flaky tests with Shaker, a joint work with my colleagues Denini and Marcelo from the Software Testing and Analysis Research Group at the Federal University of Pernambuco. First, what exactly is flakiness? Flake tests is a test that both passes and fails without any changes to the code. As an example, what you see is an actual screen of AntennaPod, a podcast player app for Android. One of the tests in this app checks whether a particular media file is being played. To play a media file, we have to perform I/O operations, such as loading the file. This way, there are assertions throughout the test code stating that we should wait for a given period of time before checking whether a particular file is being played, as highlighted in the screen. What characterizes this test as flaky is that, depending on the running environment, the test may fail or pass without any changes to the code, because this time constraint might not be met. The non-deterministic behavior caused by flakiness can make debugging very difficult to developers. Indeed, test flakiness is a well-known problem in the industry. For instance, reports from Google state that most of their test failures are due to flakiness, and that almost 60% of their tests have some level of flakiness associated. A survey with Microsoft developers found out that flaky tests are considered to be the second most important reason for slowing down software deployments. And how do developers tackle flakiness? The standard approach is rerun, that is, running tests multiple times. Sadly, this is both unreliable and expensive. Unreliable because it's hard to determine the number of reruns to find discrepancy in outputs. It is expensive because rerunning tests consumes a lot of computing power and consequently takes a lot of time. So, it is important to have early and proactive detection of flaky tests. This leads us to the core idea behind Shaker. Many tests are flaky because of timing constraints in test executions. Our hypotheses are that adding noise to the environment might reveal flakiness, and also that rerunning tests in a noisy environment will reveal flakiness earlier. But what do we mean by adding noise? Basically, we use a noise generator tool to create load. That is, the tool generates stressor tasks focused on CPU and memory to influence the execution environment where tests will be executed. Our technique then consists of two steps. In the first offline step, Shaker uses a set of tests that we already know to be flaky to search for configurations of this noise generator tool. We do this because we cannot just generate a heavy load, as this could simply crash the emulator and would make our approach ineffective. We employ different techniques based on fitness scores when searching for configurations to find good configurations, instead of simply randomly selecting them. In the second online step, Shaker uses the configurations we find in the first step to search for flaky tests on the test suite of a project provided as input. The idea here is that we run a test suite on a noisy environment for a number of times to see if there are divergences on the outputs. In this online step, there is indeed a tension between cost and effectiveness. Executing a test suite under a loaded environment will be slower compared to a regular execution, since different tasks are competing for the machine resources. Our hypothesis is that Shaker may require less executions to detect flakiness. As a result, the aggregate cost of detecting flakiness would be lower. So how did we evaluate Shaker? We have selected 11 Android projects from GitHub with almost 1,300 tests in total. We executed all tests 50 times and identified 75 flaky tests that we use to evaluate Shaker effectiveness. Since Shaker has two phases, we divided this set into two sets, randomly selecting 35 tests for the offline phase where we search for configurations of the noise generator, and using the remaining 40 to evaluate the online phase where we actually evaluate the effectiveness of Shaker to find flaky tests. So first, We evaluated the feasibility of using Shaker. Our first research question tested whether our assumption behind the core idea holds. That is, we found out that introducing noise indeed increases the ratio of failures in time-constrained tests. More, we could argue that noise generator is non-deterministic by nature, so we investigated whether we can rely on it. We observed similar rates of failures across multiple executions of the same noise configuration. Finally, we evaluate whether we need to search for good configurations for the noise generator, and our results indicate that there is indeed an advantage in searching and selecting noise configuration as opposed to randomly picking them. But more importantly, we also evaluate Shaker effectiveness. We do so by comparing Shaker with rerun. We use the 40 tests that we knew that were flaky. The results show that Shaker discovers more flaky tests in less time, as you can see in the graph. The plot quickly rises when using Shaker, and we see that we quickly saturate. In 14 re-executions, less than what we usually need with rerun, we saturate finding 85% of the total number of possible flakes. Moreover, the first execution already detected 65% of the total of flaky tests. Other than that, we also evaluate Shaker effectiveness in finding new flaky tests. So we execute Shaker for 5 hours in each project to find additional flake tests. We found 61 new flake tests in 6 out of the 11 projects. These are tests that are not signaled by developers as flaky. The results show that Flaky could reveal flakiness early, as 45 out of the 61 were detected in the first 3 runs. We also opened issues on GitHub to explain developers how we detected flakiness, pointing to a script with instructions to reproduce our steps, and some developers took action to fix or to signal flakiness in their tests. So as a summary, based on this idea of introducing noise in the environment to detect flakiness, we propose Shaker, a technique that implements this idea to detect flakiness early in a proactive way. We have evaluated Shaker's feasibility and effectiveness using 11 projects, and the initial results are promising. If you want to check out our technique, use the QR code or the repository link on the bottom of this slide. Thank you.